The simplest answer, it's that the brainstorming sessions on issues or challenges leads to innovative solutions. So when we have one problem or the other, or we are looking for ways to do something in an optimized or in a better way for efficiency, reliability, manufacturing, installation, things like that. That's what leads to brainstorming sessions, and that's what leads to coming up with these ideas. So I'll probably start with the blade. For example, the blade patent was driven or stemmed from the need to reduce the cumbersome installation process experienced with the prototype. And by prototype, I mean the turbine we have installed in Texas. And we developed this profile with a variable blade thickness while ensuring that the total area of the profile was kept constant. And moving towards a different airfoil series, NACA 0021, made a significant difference to the operating stresses in the blade. And this largely means that we do not need the additional bonded plates at the arm of the connection, which we used in M3.1, which was really a nightmare. It got the job done, but the stress was really not worth it. And that was one of the things we looked at and we say, okay, how can we make this better? And that's why we came up with the blade patent. Another example is the arm blade hinge. The hinge basically was employed to relieve the connection from flapwise or in-plane blending moment. And because of that, we're just thinking, rather than make the section bigger and bigger and bigger, which can affect aerodynamics and things like that, we just had to think about a way which would safely transfer the load or bypass the load. And that's how we came up with the arm blade hinge concept. And this also kind of directly ties to the arm mast hinge as well, which is similar to the arm mast connection. The hinge was also employed basically to reduce the in-plane bending moment and to basically reduce the size of the structural member that would have had otherwise at that connection to be able to handle the loads, the fatigue, and etc. The fairing as well was basically a lesson learned from M3.1. We're just trying to reduce the aerodynamic drag and consequently improve the efficiency of the turbine. So basically, if you are producing a different turbine from the 3.1, we want to produce a turbine that is more efficient. So this design was basically driven by ease of installation and manufacturability. We want something that's easy to install and easy to manufacture, thereby reducing drag and also increasing efficiency and reducing costs. So the other one was the X-mast. Similarly, in M3.1 prototype, we employed a forged flange. The forged flange was at 90 degrees, was a very expensive, like it was really, really expensive item. And we had it at both ends of the mast and the drive shaft. If you look at the prototype, the M3.1, you see. And so basically we were just thinking with 4.0, what can we do better? So the X-mast was designed to allow for a straight spliced bolted connection between the drive shaft and the mast. And this box is machined with hexagonal walls to match the hexagonal tube of the mast, which eliminates the need for a forged flange and weld on the mast to flange. So basically, we just wanted to get rid of the weld like we had in the M3.1, and we came up with this idea and also save costs. So two things in one, save costs and also get rid of weld. So that was the main idea. The vertical braces, they play a role in dynamics and frequency response of the system. And in M3.1, rather than have vertical braces, we have what we call cables. And the cables, you also always need to tune them or straighten them. Tension them rather. And then they also bring a lot of drag to the system, and we want to improve the efficiency of the system. So we got rid of the cable support and put in the vertical braces just to improve the aerodynamic. We need to improve the dynamics of the system and to be able to carry the gravity loads. So those are the reasons. So basically, if you see from all the invention, it's more of like, what issues do we face with the present prototype? How can we do better? How can we make the system more efficient? How can we save costs? How can we improve the manufacturability? How can we make installation easier? And this is what fuels all the different innovations and the patents we are currently working on.